So in this video we are going to look at autoencoders. The objective of this video is to look at the intuition behind autoencoders, various kinds of autoencoders. In particular, we are going to look at multi-layer perceptron encoders and convolutional neural network encoders, and there are others like LSTM and so on, but in this particular video we are going to look at MLP and CNN. So we also look into two applications. One is a denoising. We remove noise from an image, and also applying color to a gray image. So these are the two applications that we are going to look. So conceptually, like, you have an encoder part, and then you have a decoder part, and in between there is something like a latent layer, and this is where the coding happens. So in a way, if you proceed from this input layer and you are going towards the output layer, and if the output layer happens to be the input layer, so each of the layers in between are a representation of the input layer. So let's say you have an image of 784, you are compressing it to 256, you're compressing to 128, you're moving forward, and the dense layer is becoming shorter and shorter. So let's say this layer is 32 dense layer, and this code will encode all of the information that is possible within the input layer into this 32 digits vector, and you can reconstruct back using this decoder layer. So encoder is one type of function, and you get to a latent layer called Z, and then the decoder is another function that takes this Z and try to reproduce X prime, where X prime is very similar to X, or it should be identical to X. So this is a reconstructed input, and this is a given input. For example, here the image is 4 and you are reconstructing it to 4. In this case, if you look at a MLP autoencoder, you're starting with an input data and you're getting an output data. This is the reconstructed data, but you are going through this, you're reducing the number of layers, or you can increase it, and then finally you get to a point where you can take this as input, and then you can use a later layer to convert to the input form. So again, like, this is the input, like we give an input image as 6, you go through an encoder and you're representing it's a compressed representation, and you can decode. So you can easily see that this particular architecture can be used for the sake of compression, so that you can easily reconstruct the images back. So these encoders and decoders need not be only for a multi-layer perceptrons, but also convolutional networks. So in this case, it's a CNN based autoencoder, where your image is going through convolution layer transformations, and you can have a latent representation, which could be a single dimension, or it could be a multi-dimension representation, and then you are taking this input and you are reconstructing back the original image. So this is a convolutional autoencoder. Some of the applications include, you have an input, you slightly modify the input. For example, you could make some of the pixels a noisy pixel, and then you can give it to it, and then you generate a correct input, and then you go through the encoder and you ask the encoder to represent in this one, and then the decoder to get to the original form. So this output, whatever is seen here, it is compared against the input, and you are trying to minimize the loss. So how does it help is, like, if you have noise in your original image, this particular network can remove that noise, because you're expecting the output to have input. And this particular noise could be also, you're taking a color image, and then let's say you're changing it to gray through some transformation, and you're saying that the output should be a colored image. So this network will learn how to decode a gray image into a colored image. So these are few learnings usually from these images. So let's look at how to do this encoding. So the project, my project setup is as follows. You can see my project folder is in keras. You have data and notebooks and images, and if I have any scripts, Python scripts, I usually have a scripts folders as well. So how do we construct? So first let's look at MNIST data. We'll try to load MNIST data, and we are transforming it so that the values are between 0 and 1, and you can see the shape that training data has about 6,000 records with 28 by 28. So what we do in this way, so the packages that are read are essentially within the layers. You have dense layer, flatten, reshape, and input, and then we are using SGD. You could as well use Atom without any problem. So in this case, we are going to construct an encoder in a list-like format. So you're specifying a list, and with each of these lists, it contains the network design. So the encoder will start with a 28-bit image. We try to flatten it so that the input is going to be a 784 input layer. We are then passing it to a 512 input layer, then 128, and then 64, and finally to 32, which is our encoding dimension. So this is the latent layer. So this is the encoder part, and then for the decoder, will take this encoder dimension as the input, and then it will go through further layers. Like we are essentially going in reverse. So for example, here we are using a dense, we are changing it to 64 dimensions, passing through 64 neurons, and then 128 neurons, and then 512 neurons, and then finally this is our output, which was 784. So we are getting an output of 784, and each of those pixels is going to be a sigmoid transformation. So then whatever the output we can change it to 28 by 28 dimensions. So autoencoder consists of two parts. One is the encoder part and one is the decoder part. So you can specify the model as shown here, sequentially encoder and decoder, and you can compile the model with the binary cross entropy and with SGD as the optimizer and the metrics. So one important thing that you change is that, as the definition says, it's autoencoder. So it's trying to give input as xtrain and also expecting the output as xtrain, and the number of epochs is going to be 5. And then the validation data set I'm giving as x test and y test, just to see how it's performing in this particular data set. But as you can see, it's nothing to do with the y value. So autoencoders is essentially the input, and we are trying to regain that input after a series of encoder, latent, and the decoder part. So in this case, when you run it, you can see the validation loss is changing from 0.21 to 0.11. I'm only running 5 iterations, and the accuracy is not a lot. You can see it's 0.24. So it didn't really do a good job, but we can still see what it has done within this 5 epochs. So to do the predictions, I just took the, this is like any other neural network. You're using autoencoder and you're calling predict function on X test. So it is going to do predictions all 10,000 images. So I'm taking this particular resultant data set and I'm plotting here, right? So the original data is X test, which is what is asked to be, we try to predict, and then the predicted images here. As you can see, the first row indicates our X test initial image, the 10 images, and then these are the predicted. It did a fairly good job. It's almost, we can easily read it. I mean, in some cases, I think the 9 looks somewhat blurred, and maybe even the 5 looks blurred, but definitely it did a decent job in reconstructing the input image. So let's look at convolutional based autoencoder. So we will start with actually this one. Okay. So we are still using the same MNIST data. We are, however, So the input shape, so we are again constructing two parts, like encoder part and the decoder part, and we are creating autoencoder by combining encoder and decoder, and the rest of the code is more or less similar. So you don't need to do build and summary, you can actually fit it directly, but I used it so that I can print summary here. So what we did in the encoder part is we had a input layer, and then we are transforming this input layer into 32 dimensions filters, convolution layer with 32 dimension filter, and then we are doing max pooling while all the way we are maintaining the dimension as same. So we did the same thing again with decoder. So instead of using max pooling, which will reduce the dimension, here we are using upsampling, so it will increase the dimension. So we are going in the reverse order here. So remember, this is our latent structure, and then this part we are going in reverse direction. So convolution, we are doing the same thing. Instead of doing max pooling, we are upsampling, and we are doing the same part again. So in the finally we are converting into original format by doing a convolution and 1,3. This will result the output in 28 by 28 by 1. Right. So so again we are giving x train as input, and then we are passing through it. So now when we run this one, you can see in fact the accuracy, it starts with 0.81, so which means it's actually doing pretty good in terms of reconstructing, and the loss is also, it starts with 0.08. After 10 iterations, you can see accuracy is about 0.814, and if you try to look at these results again, so I try to rerun this one again. I think the loss is 0.06, and then accuracy is 0.81. When I try to look at the result, the predicted images are autoencoded.predict. So because this is our model that we just ran, and then if you look at the results, they are almost identical in every respect. When there are slight differences, there is a little bit more blur here, but they look identical, which means it was able to reconstruct very well. So how can we use this? There are a couple of applications that I will show, where we will try to add some noise and then try to reconstruct the original image. So if you remember this particular image, what we are going to do is we are going to take the input and then add random noise to it, and then we will ask the decoder to get me back the original input, which means we are asking this network to remove this random noise. So the first one is a denoising application. So everything is very much the same thing. So we had because we are using a convolutional neural network, we are transforming our input data set into 28 by 28 by 1. We are specifying, expanding the dimension to 1, because for convolutions we have to specify a channel. So the input data is changed. The output, we are adding some noise, so there is a noise factor, and then we are generating a value between 0 and 1 from a Gaussian distribution, and then we are changing the pixel values. So but there will be some values that are beyond 1, so I'm clipping them to between 0 and 1. So the encoder code is very much similar to what you have seen before for convolutional, and also the decoder code is very much similar to the previous one. So the only the change that you would see is what we are providing the input as. So we are providing train noisy, but we are expecting the output to be the train. So this is noise. So let's look at actually how the noisy data looks like. So this is how the noisy data looks like. It's almost, in some cases, it's not actually easy to identify what these images represent. But we will try to run through the encoder and see what the outputs are going to be. So it ran again, and then the accuracy about 0.81. 0.36, the loss is 0.09, which is decent. And then I'm trying to plot the noisy image and then the predicted image. As you can see, compared to the original image, the noisy image, the reconstructed image is very clear. So this is quite useful in many applications. Maybe if your JPEG images, some of them are damaged for some reason, and then you're trying to reconstruct, this particular network can definitely help remove the noise and get back the original image. However, you need to have a clean data as well, because that's where you're training it. So another application is coloring a gray image. Instead of adding noise, we are going to convert our input image to a grayscale image. So to do that conversion, we are loading a C410 dataset, and then we are converting, we wrote a function that converts RGB to gray. So OpenCV has this formula about to convert to gray, you are multiplying about 0.3 times red, 0.6 times green, and 0.114 times blue. Right? So that's how you can convert. So this is my input data, and if you plot the gray data, just you just call the function and you get the gray input data. So you can see this is a color image of a car, and then this is a gray version of it. These images are like 32 by 35, that's why they look pixelated, but you can get an idea. This is a car, this is a gray colored car, this is a red, and this is a gray colored again, right? So let's look at what can be done. So we are getting the gray conversion images, and then we are dividing by 255, and then we are shaping them into channel 1. The gray images are expected to be channel 1, and where the colored ones are 3 channels for R, G, and B. So we are dividing them by 255, and then we are encoding them. We are using the same convolution 32, but here we are going a few more steps, like we are using 32 filter, then 64, and then 128, and then here we are generating our latent version of it. You can still do some transformations, like for example you can do flatten and create a single dimensional vector, but I just left it here. So you are reconstructing it back by using convolution 128. So in a way we are going in a reverse direction. So we did that, we did that, and then finally converted into 3 channels. So this last output is important to remember. This is not easy to understand. So this 3 is where it's generating the channels. So whereas in the previous run for convolution we used a 1 as input. So the input dimensions are going to be actually, in fact, grayscale. So it will be 32 by 32 by 1, and the output will be 32 by 32 by 3. So you can so here you can see the steps are very much similar to what we have seen before. So the input, we are passing it as grayscaled input, and then we are expecting the output to be X-train. So we ran 10 iterations, and I'm here plotting 3 images. So this one is the original image. It's hard to see because they are pixelated. Even if I try to magnify, I think they will be even more pixelated. But you can see that this is a grayscale conversion, and then this particular program tried to convert into a colored image, and you can see it's not completely, it didn't do a really good job, but in some cases you could see that the background has become blue here. These are somewhat like brownish color. So it did some coloring, but because these images are small size, you cannot see the clarity of it. But definitely this is the approach to change a grayscale image into a color images. If you have a large amount of data like ImageNet data, you can do this process very well. After training through all of them, you can introduce some new images and convert them into colored ones. Like you can give any grayscale image that you have from perhaps from 1950s or 60s, and you can pass through that this training, and you can generate a colored version of it. So let's wrap it up by concluding what we have looked in. So we looked at some concepts of autoencoders, some images, and then we looked at how to do a encoder decoder network using multi-layer perceptron, and then we did it using a convolutional neural network, and then we looked at two applications, namely denoising applications, and then